Alright, here we go. Let's take this section home. So we are talking about osmosis and osmotic pressure. And so osmosis, well, this is the uneven flow of solvent through a semi-permeable membrane. And if that seems like a whole bunch of garbled gibberish mumbo jumbo, I'm going to draw an amazing picture. It's going to change your life forever. You'll frame it and put it up on a wall or something. At least a refrigerator. So uneven movement of solvent through a semi-permeable membrane. That is a dry definition, right? So first, what is a semi-permeable membrane? So we're going to break this down. So a semi-permeable membrane it's a barrier that only lets solvent through. So maybe water passes, but salt doesn't. So solutes don't go through it, just solvent. So only solvent passes through the membrane. And that's what makes it semi-permeable. Permeable would be like everything goes through it. And it's like, what the heck kind of membrane is that? Semi-permeable holds back everything but the solvent, which for biological systems means water. And so why do we care about this? Well, cell membranes are semi-permeable membranes. They have passive transport for water, so they let the solvent flow through equally. Everything else has to be actively moved in or out of the cell. So we can move sodium ions in and out of the cell, but we have to pump them out or pump them in, whereas water can just flow freely. So we'll talk about that more in a little bit, but keep in mind that cells' membranes are semi-permeable membranes, therefore osmosis occurs with cells, and they will experience osmotic pressure, which we'll talk about in just a minute. So that's what osmosis is. We get this uneven movement of solvent, and so what can happen is we get a pressure. If you have an uneven movement of solvent, you start packing more solvent into a cell, it starts to try to expand, it experiences a pressure, and it can burst if there's too much. We'll talk about that more later too. But that pressure is called, very creative here, osmotic pressure. So we'll start out with a couple definitions and then the life-changing picture that you'll never be able to unsee. So, this results from uneven solvent flow across a semi-permeable membrane. Okay, barely squeeze that on the page. So semi-permeable membrane. Hope you're enjoying it's like midnight. I'm still making videos, I'm trying to get these knocked out. So I hope you enjoy my midnight handwriting. And if you're thinking, I paid a lot of money for this class, I deserve better than midnight handwriting, I agree. You're right. But you haven't changed my mind, so we're going to keep going. Plus you get all the good stories out of me when I start getting tired. I mean, I should have a better filter than complain about the worst student I ever had on the internet, but you know, how could that ever come back to get me? So, uneven concentrations of solutes are what drive this. And again, next page, I promise, there will be a picture. Less words, more pictures. That's how we do it. It's how we do it in America in 2020. Or whatever year you're watching this. Probably not 2019, because those were simpler times. So, uneven concentrations of solutes drive this uneven solvent flow. And so they generate osmotic pressure. So if both sides have equal amounts of solutes, there's no osmosis occurring, there's no uneven flow, there's no osmotic pressure. That's what we're saying here. So what it's trying to do is make both sides the same concentration. That's what's trying to happen. So it's trying, if one side's more concentrated than the other, it's going to try to add more solvent to it and equal those concentrations out. It's going to raise one side and lower the other by moving solvent. And so what does this look like? Well, like I said, cells do it, but this is chemistry class. I'm not drawing a cell. I'm going to draw two beakers attached by, I don't know, straw. Look at that right there, you know. That's what like 6 weeks of elementary art class will get you. And then we've got this guy right here. And I have a very, very modern type of art that I draw. It's my technique. It's called postmodern arrow pointillism. And that's because I'm going to have an arrow pointing at everything, labeling what it is. So this is our semi-permeable membrane. How do you know it's semi-permeable membrane? Because I have an arrow pointing at it that says semi-permeable membrane. That is the beauty of postmodern arrow pointillism. So, if I have two solutions here, I just set this up, and I have water over here, and I have water plus, say, sucrose, table sugar. There are no solutes here. There are solutes here, so they have an uneven concentration, so osmosis is going to occur, and it is going to flow from low to high concentration. So over here is my low concentration. This is my high concentration. And so my solvent is going to flow more to the right than back to the left. And so what happens is this water level goes down, this water level goes up, and eventually it stops happening. So water is moving back and forth, just not equally. There's more moving to the right than the left. And then eventually it evens out. In terms of the flow, the water levels aren't even. They're like this. Now, I can't get these two to be the same concentration, so why does the water stop flowing to the right? Why doesn't it just all go over there? Well, gravity's pushing down on this water. And so as the height gets out of the way, gravity starts exerting a pressure because one side's taller than the other. So, you know, naturally, if you just had a valve and you opened it, if you had two containers, they would equalize without a semi-permeable membrane. And so gravity's pressure equals the osmotic pressure, and we get a height that stays stable. And so we see this over and over again. This is a technique that's used, or the opposite of it is used, excuse me. It's called reverse osmosis. We actually force water back through one of these membranes, and we can purify it. So it's something that California is doing a bunch, so you can turn ocean water into drinking water. And they've developed a few tricks to make it more energy efficient. So it's the most efficient way to do that. And it only costs a cool $1 billion a plant. So California said, we'll build 7 of them, because what? $7 billion to the 5th largest economy in the world. Full of a bunch of thirsty people. And almond trees, too. Can't forget the thirsty almond trees down there. They're almost more important than the people sometimes. So, get the water levels to change. Any of my students from California right now are thoroughly upset, and that's fine. Whatever. We got plenty of water in Oregon. Unfortunately, I'm moving to Arizona, so I don't get to brag about water on California anymore. Well, that's the polite way of putting it. There's no ocean to desalinate in Arizona, that's for sure. Not unless it really moves up. Well, ocean levels really rise. So we get this, uneven flow. We get a pressure. We get osmosis. We get osmotic pressure. Now, it's proportional to total dissolved particles. So, osmotic pressure is proportional to the difference in total dissolved particles, which is known as osmolarity. So for example, one more drawing here. If we have a setup we got our semi-permeable membrane. How do you know? Postmodern arrow pointillism. We got a solution here. Here, let's say this is 1 molar sucrose. This is 1 molar NaCl. Is there going to be osmotic pressure? Is there going to be an uneven solvent flow? Now the answer is yes. You go, well, this is 1 molar, that's 1 molar. Okay, that's true. But sucrose is a sugar. It's covalently bonded together. It does not dissociate in solution. You dissolve a sugar, you get 1 dissolved particle. But if you dissolve an NaCl, what this is saying is we have 1 molar Na pluses, because it's an ionic compound. Think back to the attractive forces section or solubility, I talk about this. And 1 molar chloride. So if you see an ionic compound, realize all the ions separate when you dissolve it. I'm not going to show you any insoluble ionic compounds. I'm not going to try to trick you guys. And so if we add that up, it's 2 molar total. That's our osmolarity. It's all the stuff dissolved. So if you don't have an ionic compound, osmolarity and molarity are the same thing. If you have an ionic compound, it's all of the ions put together, all their molarities add up. So so total dissolved particles, 2 molar. And so that means we're going to have solvent flow this way. And so we are going to have an osmotic pressure over here because this column is going to move up. This column of water is going to move down. So that's what we're looking at. Alright. So it's a little bit tricky. Take some time to think about it. Like, print these out, put these on your refrigerator. Your life will forever be changed. You can even tell your parents you drew it, and they'll be like, has that been up there for like 15 years? Was that, what, 2nd grade? And then you go like, how dare you? That is a scientist's representation of what's going on. Professional scientist. How dare you? Alright, so one last section to talk about here, or one last idea in this section, excuse me. And that is going to be applying this directly to cells. So I mentioned earlier, cell membranes are semi-permeable. And if we look at like red blood cells, so they're floating around in the bloodstream, they're just bouncing around. As long as you don't have something like sickle cell anemia, they're kind of tube-shaped, they bounce around. If you have sickle cell anemia, they can go kind of like a sickle shape and get stuck, and it's very painful, and I feel for anyone that has that. It's not fun. But under normal conditions, you have that normal kind of it's not a donut or a tube because it does have a middle, but it's sort of, it gets a little thinner in there, looks a certain way. Has a nice shape. Literally, it's, you can think of it like oxygen is tubing in the river of your bloodstream. Like the red blood cells are the tube carrying the oxygen around. If you've ever intertubed a river. If you haven't, I highly recommend it. Just, don't use any given river. Make sure there's no big waterfalls or anything. It can be a little too adventurous if you don't scout ahead. And you gotta watch out too for fallen trees are actually the most dangerous thing. So you want to make sure you've got a good patch of water that a lot of people are doing that type of thing in. Don't just be like, oh, there's a river, I'm gonna tube. I want to be clear about that. And then don't get too comfortable in the tube either. So it's got that hole in the middle, and you can sink down, and then bam, that's when a rock gets you in a place where you'll feel it. So you got to kind of keep your butt up a little bit in the water. That's a professional tubing tip there from an amateur. Okay. So, red blood cells, that's what we were talking about. They are going to depend on the environment. And by environment, I mean bloodstream. Having the correct concentration of solutes. Correct, I'll say total concentration of solutes. And this is known as tonicity. So, this is kind of Goldilocks in the three bears here. There's going to be something that's bad, something that's good, something that's bad for a different reason. So, if there are not enough solutes in our bloodstream, so it's a low concentration, then what's going to happen? Well, if it's low concentration outside, high concentration inside, water is going to flow into the cell. That's what's going to happen. So water flows into cell, causing swelling. And so, it's just like, it's like an inflating balloon. And at a certain point, it can't get any bigger, it can't swell anymore, so it just, it ruptures. So it causes swelling and potential rupture, which is not ideal. I'm going to give you a hint. Red blood cells, when they rupture, tend not to function, so that's a problem. So this is a hypotonic solution. Alright. Now, if we have the right amount, then we have normal shape, we have normal function, there's no osmotic pressure on the cell, excuse me. Everything's fine. So, if solute concentrations are correct, so I'm getting a little shorthand with concentrations, just be aware. And that's about 0.28 molar. That's what we want in our bloodstream. Then there is no osmotic pressure on the cell. So we get normal shape, and it's a lot like proteins. Shape and function go hand in hand here. So normal shape and function. And we call this isotonic. Alright, and then the last one. You can probably guess what it's going to be, by the way. Too low, just right. And then what do you think is going to happen in this next situation as well? So what is it? Well, if concentrations are too high, that's a problem. So we go over over 0.28. Then we have more concentrated outside than inside the cell, so water is going to flow out of the cell. Right? It's going to go from high to low concentration. From low to high. I was thinking of diffusion for a second, which is different. So in osmosis, the solvent is going to flow from low to high concentration, because it's going to try to increase the concentration of the cell by shrinking the volume, by getting rid of water. So if concentrations are too high, then water flows out of the cell. Okay, so it's flowing out of the cell, and that's causing the cell to shrink. It's going to shrivel up. It's going to be like a raisin. And what can happen is it can shrivel up and get stuck that way. And so just, and that's it. That's a dead cell. There's no reinflation. It's done. It can shrink a little bit. There's some wiggle room there. Just like it can expand a little bit before it ruptures. It can shrink a little bit before it gets completely crumpled. And just stuck, crumpled. But it causes the cell to shrink and shrivel up. And so we had hypotonic, isotonic. We had hypotonic, isotonic. This is hypertonic solution. So this is why when you give IV drips, use a saline solution. You don't want to add just pure water, because that's going to throw off the concentration in the bloodstream, and then you're going to start having issues with cells. If it's just pure water, it's going to dilute the total dissolved solutes in the bloodstream, and that's going to cause, a hypotonic situation where the cells are going to rupture. And if you had something that was too strong, then you get the opposite, and the cells start shriveling up. Either way, it can cause tissue damage, and so you want to avoid that. So you want to make sure that, so that's why we give saline drips, and not just water. So that's it for this section. Osmosis is a little bit tricky, but remember, behind it all is that semi-permeable membrane. And why are we talking about it? Well, cells have semi-permeable membranes, so they can experience osmotic pressure and have hypertonic, isotonic, hypotonic solutions around them. So we'll leave it there. This was a long section. I talked about a lot, but I think it's 75% helpful, and then just 25%, putting life back in you before you take the test that you're studying for. And this is the last section for the exam 2. So just a reminder that exam 2 will start with section 9, attractive forces, and carry through 17. So I think there's 8 sections here to study to make sure you're familiar with that are all fair game for exam 2. So if you're reviewing and you have questions on any old stuff, don't hesitate to ask, as well as the new stuff we're talking about here. So happy studies, and hopefully my stories cheered you up, or at least put the fear of me talking about you one day to my classes in you, so you behave. Either way, it works for me. All right.